Hey everyone, and welcome to this explainer. Today we are taking a really deeply fascinating journey straight into Chapter 3 of our source material, which is all about plane similarities. We're going to unpack the shifting, bending rules of geometry that govern exactly how shapes transform, scale, and even spiral across a flat plane. It is this incredible, almost magical mathematical landscape, and honestly, I am absolutely thrilled to guide you through it.
So, to kick things off, I want you to consider a pretty fundamental question. In standard Euclidean space, we're all so used to symmetries, right? Like simple translations or reflections, where the distance between points never ever changes. But what happens when we just throw that rule completely out the window? What happens when we explicitly design a transformation that breaks the rules of distance? Well, that exact question is the doorway into the entire concept of geometric similarities. And here is our roadmap for today. We'll start with the stretching factor alpha, move into the classification theorem, explore the magic of spiral similarities, then look at partial transformations, and finally, wrap up with squaring and circular inversions. All right, let's dive right into section 1, the stretching factor alpha.
Okay, so meet the stretching factor. In math, we denote this with the Greek letter alpha. In basic geometric terms, a similarity is just a plane transformation where the distance between any two points is multiplied by this exact positive number, alpha. Now, if alpha is exactly 1, the distance doesn't change at all. That means all those classic symmetries you already know about, they're actually just special, highly restricted similarities. But when alpha is greater than or less than 1, well, that's when things get really dynamic. Let's track how this actually looks. Imagine fixing a point O right in the center. Step 1. Point A slides outward along its ray to a brand new position, let's call it G of A, and it exactly doubles its original distance. Step 2. Point B does the exact same thing, translating out to G of B. Because the angles are mathematically preserved here, and the sides have grown proportionally by a factor of 2, this new triangle is perfectly similar to the original one. The distances have definitely increased, but the fundamental shape, it stays exactly the same. And keep in mind, alpha doesn't just make things bigger. If we set our stretching factor to a fraction, say 1/2, the entire plane actually pulls inward. You can see how a central similarity with an alpha of 1/2 drags points A and B closer to that center point O. This proportional scaling, whether it's growing outward or shrinking inward, is really the heartbeat of a central similarity. Which brings us to section 2, the classification theorem. So the absolutely crucial point here is that every single similarity on a plane, literally no matter how incredibly complex it might look, must mathematically fall into one of 3 exact categories. It's either a standard symmetry, where distances are preserved, a spiral similarity, or a dilative reflection. There are 0 other options. The entire infinite plane of possibilities is contained right here in these 3 little buckets. To really understand these categories, let's break down the mechanical steps of a dilative reflection. Step 1. You apply a central similarity, meaning you stretch or shrink the points outward or inward from a fixed center point. Step 2. You immediately reflect those newly scaled points across a specific line passing straight through that center. So it's a very precise sequence of scaling, instantly followed by an axial flip. Okay, moving on to section 3, the magic of spiral similarities. Now, what if we swap out that reflection for a rotation? Step 1, our central stretch pushes point A out to a new spot. But then, step 2, we apply a precise angular rotation around that exact same center point to land at our final destination. So the end result is a mathematical product of both distance modification and rotation. The real visual payoff happens when we iterate this. If you take a single point and subject it to that exact same stretch and rotate transformation 12 consecutive times, well, you can literally mathematically track the geometry pulling the points outward and rotating them simultaneously. It charts out the undeniable, beautiful beginning of a spiral. But what happens when we apply extreme mathematical precision to this sequence? The source material takes the stretching factor way down to a tiny 1.01, so it's barely growing at all, and locks the rotation angles strictly to the golden ratio. When you plot 310 consecutive points doing this, the patterns are already starting to weave together in this mesmerizing way. And if we zoom out and just let the math run for 910 iterations, the complexity explodes into pure natural perfection. Look closely at this structure. Because we use the golden ratio, the resulting points naturally align into exactly 13 distinct spirals winding clockwise and 21 winding counterclockwise. 13 and 21. Those are perfect consecutive Fibonacci numbers, just dancing right there across the mathematical plane. Incredible, right? This brilliantly illustrates how rigid academic definitions of spiral similarities can directly birth breathtaking visual art. What you're seeing is Mark Thompson's sphere spiral cluster from 2003. It's not just a pretty picture, it's a direct visual manifestation of the exact stretching and rotating formulas we've been unpacking. The math literally becomes the medium here.
Let's shift gears a bit. Section 4, exploring partial transformations.
The contrast here is super foundational. Up until now, every similarity we've talked about acts on every single point in the plane. No point gets left behind. But partial transformations, they are the geometric rule breakers. Under a partial transformation, there are certain points, very often the center point itself, that simply have no mathematical image at all. They're left completely undefined, basically just dropping off the map entirely.
And that brings us to our final section, squaring and circular inversions.
First up is the squaring transformation. Take a point, measure its polar coordinates, meaning its angle and distance from the center, and apply a strict new rule. Multiply the angle by 2 and square the distance. Unlike those similarities from earlier, which nicely preserve angles, squaring distorts the foundational shape entirely. It turns it into a completely different geometric beast. Then we have circular inversion. This is this elegant sequential animation that practically turns a circle inside out. Step 1. From a point A, inside the circle, you draw a perpendicular line to the line connecting A to the center. Step 2. Right where that perpendicular hits the circle's outer edge, you draw a tangent line. Where that tangent intersects your original center line, boom, you've located your inverted point. Points inside map to the outside, points outside map back inside. But that center point, it remains mathematically undefined forever. Real quick before we finish, the source text does briefly note one more highly specific mapping, the linear fractional inversion. It basically takes that inside-out inversion process we just saw and layers a translation right on top of it, mapping a point to a new, inverted, and translated location. It's a really complex, multi-step geometric maneuver that perfectly caps off our academic breakdown of plane transformations today. As we wrap up this explainer, I want to leave you with a pretty provocative thought. We spent all this time looking at flat 2D planes, stretching them, spiraling them, turning them inside out. But geometry obviously doesn't stop at the page. Imagine just for a second standing in the room you are in right now and applying a full 3D circular inversion to your reality. The center of the room just disappears into nothingness, the walls push out to infinity, and the distant horizon folds right into your lap. The rules of geometry literally dictate our reality, and when you learn how to bend them, the whole world looks completely different. Thank you so much for exploring with me today. Keep questioning the space around you.